title of this talk is Strange Saga Number Theory. You'll get dinner afterwards. Contact me after the talk.
Okay, it's my pleasure to be giving a second talk here. The two talks that which I gave abstracts, I should say the two abstracts for the two talks were written to sound essentially isomorphic or identical. The talks are actually quite different, although they have a parallel in the sense that both began roughly when I was 16 years old, and each of them was then continued at some, well, there was a certain exploration that went on for a while with different degrees of intensity for several years, and then sort of faded out, and then it came back into existence, or into my world, some either 1, 2, or 3 decades later. And so, in a strange way, both cases with somebody whose first name was Greg or Gregory. And so, yesterday was Greg Huber, today is Gregory Wanier, my advisor in physics. All right, so I'm going to begin by talking about some stuff that I did when, as I said, I was about 16, and I was very excited by number theory, and I was persuaded that I was going to be a number theorist, and my first exploration in this domain was actually triggered by a question that was posed to me by a New Jersey mathematician, who some of you may know, John Mather of the Princeton University Math Department. John and I were friends when we were little children, because I grew up partly in Princeton, then we lost track of each other for a while, but in our teens we got back in touch and we exchanged letters, and he asked me some questions about triangular numbers. And that got me interested in the nature of triangular numbers. And so here is just a picture to remind you of the standard fact that the nth triangular number is n times n plus 1 over 2, a quadratic number. For reasons that I don't actually recall, I asked myself the question, what is the distribution of the triangular numbers relative to the squares? So I wrote out, and this was all done originally by hand, and then it was done using a Frieden calculator, one of those mechanical, semi-electronic, not electronic, electrical chugging computers or calculators back in there. This was in 1961. So I've written the triangular numbers in red and the squares in blue, and just giving you a sense that what I was interested in knowing is what is the distribution of triangulars relative to the squares. So there are two in this interval. I would draw my line right there. My barrier is just to the left, but they coincide, like with 36. I would put it to the left. And so there are two here, 1, 2, 1, 1, 2, 1, 2, 1, 2, and so forth. Now, I calculated this sequence out for quite a long distance. And so here are some terms of it. And I could see, I was being very empirical, in the same spirit of as yesterday's talk. I was doing a lot of empirical stuff. I also did, some proofs. But at the beginning, I was generally guided just by my interest in patterns. And so I was looking for patterns, and I wasn't trying. I mean, of course, I did write down the formula for the nth term of the sequence, but the formula wasn't transparent, and so I then started looking at the sequence itself and to see if I could find some properties of it. By the way, that little comment anticipates something of interest, which is an interest in numbers as opposed to trying to manipulate formulas, which comes back later in this talk. It is something that served me well in my later incarnation. So, if you look at this now, admittedly today, people are familiar with the kinds of structures that I discovered at that time in such a way that they're going to be much less surprised than I was. But for me, there was an immense amount of surprise when I found some structure here. Firstly, it didn't seem to be periodic, and if you look at it and try to find the periodicity, you'll find that it doesn't have any. But I naturally, my eye was drawn to the fact that the sequence consisted of, I mean, this is a visual phenomenon, you understand, was sort of what you could call 2 11s and 21s. That's how my eye picked up on it. And so, for reasons that are obscure to me now, what I did was I sort of put circles around the 2 11s in my mind, or on paper I would rather do it, and then I looked at what was in between the 2 11s, and here there was a 21 and 21, here's a 21, there's a 21 and 21, and so forth. And the obscure thing that is, I don't know quite why I did it, I wrote 4 here, meaning there's 2, 1, 2, 1. And then 2, 1, I wrote 2. And then 2, 1, 2, 1, I wrote 4 again. So I came up with what I call a derivative sequence. And the derivative sequence was composed of 4s and 2s. And I looked at it for quite a while, and after a long time, it occurred to me that I could divide it by 2. And when I divided it by 2, I found that it was 2, 1, 2, 1, 1, 2, 1, 2, 1, 2, 1, 1, 2. I found the exact same sequence as this original sequence. And it took me a couple of days of intense exploration to find this. Now, at the time I was doing this, 1961, Stanford University, which is where I was, had one computer. They didn't really own it. It was owned by a bank in San Jose, and Stanford was allowed to use it in the evenings and overnight. And it was in the comp center, as they called it. And a friend of mine, who was of my age, knew how to program. He taught me how to program in Algol, and it was a Burroughs 220 machine. And it was in the basement of an old rundown building, if you know Stanford, Encina Hall. Stanford. But anyway, it was in an obscure place on campus, and virtually nobody knew about its existence. I was one of the handful of people who frequented the comp center in the basement of Encina Hall. And so I would ask the computer to calculate terms of sequences and to verify hypotheses for me, and I did it very passionately for several years. And this was, of course, the first one, and it was extremely exciting to me. Eventually, I did prove this result, although it took quite a while to prove it, because a lot of things had to happen before I was able to reach that point. I was interested, after I had done this, in having the same experience again. I wanted to, as mathematicians always do, they want to generalize, and they want to find a larger pattern, of which the original pattern is only the tip of the iceberg, you might say. And so I thought to myself, well, triangles and squares, what the obvious generalization is pentagonal numbers, and so there's a natural way to write down pentagonal numbers. You can think of it algebraically or geometrically. If you think of it algebraically, the differences, the second differences of the first sequence are 1, the second differences of the second sequence are 2, the second differences of the third sequence are 3, that is 4, 7, 10, 13, 16, etc. However you want to think about it, you get some more, you get a new family of polygonal numbers for n. And so then it occurred to me, to try to count, well, I wasn't sure if I wanted to count triangulars between pentagonals or squares between pentagonals or what. And I tried it out, and I got sequences that were somewhat similar, but they didn't have the property, at least I didn't discover any property that would show something being equal to its own derivative. And so I was hunting around for more variations. I mean, this is my first set of variations, but then I went out in different directions. I decided to replace the plus signs by times signs. And I did it again, and I got 2s and 1s again, and And trying to remember. I don't somehow, oh, I see. OFF stands for odd number product, factorial, factorial, odd number product, factorial, factorial. And so I got pages and pages of output that looked like this. And I wrote this little poem, rows after rows, and troughs after troughs, and F's after O's, and ofs after offs. Again, there was a lot of pattern, but not enough, and there wasn't anything like the properties that I found the first time. And so I kept on looking for more. I reached out into other areas of semantic space, you might say, trying to generalize. And the next one was counting powers of 2 between powers of 3. And that one was actually, the formula was easy to find because the number of powers of 2 below any number is the greatest integer, that's the floor function in log to the base 2 of the number, and so the number of powers of 2 between x and y is this, and if y is a power of 2, then you can simplify it to get this expression, where alpha is log to the base 2 of 3. And so I got, this was the nature of the sequence that this is the algebraic nature of the sequence that this operation gave me. And so, although you may not be able to read this, it will give you a sense for it anyway. The top line consists of 1s and 2s, in which 2s are more frequent. Then the second line consists of where I'm counting the number of 2s in between 1s. In other words, the 1s occur only isolated, and the 2s occur in variable amounts. The 2s occur either doubly or singly. And so the second line, which is in red, I don't know if you can see it or read it. Can you read it at all? Some of you, anyway. The second line consists also of 1s and 2s, but it's not by any means the same sequence. But in the second line, the 2s are the rare ones, and the 1s are the common ones. So the roles are reversed. Then I did it again. I counted the more frequent ones between the isolated ones, and that gave me the third line, which is in light blue. And it's again consisting of 1s and 2s, but tamper-like, even though it is, it's nothing related to the previous 2 sequences. And now the 1s occur in, well, you can see it for yourself. I don't want to narrate this down to infinite detail. What's interesting is that finally, on the 4th iteration of taking this kind of a derivative, I wound up with some sequences that weren't composed of 1s and 2s, but of 3s, and I don't know actually what the next number is. It might be 4s. Whatever it is, it's some integer, and it's 3 and either 2 or 3 and 4. What I saw here was that I was sort of getting into a this idea of taking the derivative was a very interesting idea. Taking the derivative of a sequence that was of this form, and it looked as if it was another sequence of this form, and as if I could continue taking derivatives forever. Now, what's interesting to me, what I remember extremely vividly at this time, I want to see what my next transparency is in like. Okay. I remember I went to my mentor, Gordon Latta at Stanford. He was, what's going on? I went the wrong direction. I went to my mentor, Gordon Latta, and I asked him, I told him about what I was doing. He was very supportive. He said it was very interesting. And I had this formula, the k plus 1 times alpha, floor of, minus k times alpha, floor of. And I said, where alpha, by the way, was log to the base 2 of 3. Alpha was a particular constant. And I said, I think I have to explore, log to the base k of n instead of log to the base 2 of 3. And the reason I did that was that I was a very discrete kind of a person, ETP, not EET. And the origin of my exploration had been in counting powers of one integer between powers of another integer. And so it occurred to me, so the way I perceived the expression log to the base 2 of 3 was that it was a function of 2 integers. It was a function of 2 integers. And that's how I perceived it. Well, when Gordon looked at it, he perceived log to the base 2 or 3 totally differently. He just said that's a real number. He just saw it's a real number. He said, just let it be any real number. And of course, actually, when you think about it, it sort of makes sense, because the logarithms of the expression, the set of numbers that are formed log to the base k of n is dense on the real line. So you might, essentially, you get almost every real number anyway. You don't get it. It's countable, but what I mean is you get arbitrarily close to any real number, so you might as well just let it consider for all real numbers. And that was, for some reason, I don't know if I would ever have thought of that idea, but he suggested it. And so that was a takeoff point for me. So now alpha became an arbitrary real number. Actually, I was mostly interested in irrational numbers, not rationals. Because then the derivatives would go on forever. If you did it for rationals, the derivatives petered out at a certain point. So I just am going to make a couple of definitions. The C of A is the closest integer to alpha. So let's take as our example pi. So if alpha is pi, then the closest to the count, as I call it, C of A, the count is 3. And S of alpha is the second closest integer, which is two integers that surround the number, so that's 4. So those are the two numbers that the sequence is always composed of. And the sep, as I called it there, I called it that because it's a separator. It always occurs isolated. Whereas the count is the thing that occurs in different clump lengths. And so you count the number of counts between seps, and you get a new eta sequence. So here's just some examples. So you take pi, the count is 3, and the sep is 4. You take e, the count is 3, and the sep is 2, and so forth. All right, so one of the first things that I...
Sorry, the question?
Yeah,
I was just saying, how do you take sep of an integer? Because the second closest...
Oh, I don't worry about exceptional sets of measure 0 like integers. I was only conservatively irrational.
Okay.
Yeah, you can always... I mean, effectively, what happens is at the end, you wind up with an eta sequence that's sort of trivial. It's just like 5, 5, 5, 5, 5, 5, 5, 5, 5, and that's not very interesting. I was only interested in ones that could be differentiated forever. So, so this is just showing what I just said. Effectively, that the seps, which are in blue there, occur isolatedly. The counts occur in groups of different lengths. And in fact, the derivative sequence is another eta sequence of the, well, I call these things eta of alpha. Eta of alpha is that expression k plus 1 times alpha, greatest integer, minus k alpha, greatest integer. So that's an eta sequence. And so the top one is an eta sequence belonging to some unknown thing. The second one is also an eta sequence. So the derivative of an eta sequence belonging to alpha is the eta sequence belonging to alpha prime, where alpha prime is derived from alpha by this simple formula, the sep minus alpha over alpha minus the count, which basically is just saying here's two integers flanking alpha, and you just take the distance to each of its neighbors, and integer neighbors, and you take that ratio, and it's always at least 1. And if it's irrational, it's always greater than 1. Okay. So that gave me this whole world to explore. What happens when you take derivatives of a given real number? So that's what I call the vertical structure. So from alpha, you derive the count and the sep. From the top row, then you can derive alpha prime, from which you can get the count and the sep of that. And then you can get the third row, and you can get the fourth row, and you can continue indefinitely. So I wanted to explore this. Being an empirical math person, I decided, well, I just give you some examples to be sort of trivial. It turns out that when it's the square root of 2, the derivative is this eta sequence derivative is also belongs to the square root of 2, which just immediately gives itself back. And so the count sequence vertically is just all 1s, and the sep sequence is all 2s. You might ask how frequent that is. Well, for the golden ratio, it's the reverse. For the golden ratio, the counts are always 2. That is, phi is always equal to phi prime, phi double prime, phi triple prime. They're all the same. They're all phi. And so the counts are all 2 and the seps are all 1. And in that sense, the square root of 2 and phi are complementary numbers. The sep column of 1 is the count column of the other, and vice versa. Okay. I asked myself questions like, what about famous constants? What are their count and sep columns? So I began with E. I don't know if I began with it, but I certainly explored it. And this was what it looked like. Now, on the left, 3, 1, 3, 4, 1, 6, 1, 8. On the right, something came out that looked very interesting. 2, 2, 2, 3, 2, 5, 2, 7, 2. And being a naive 16 or 17-year-old at this point, I said, oh my God, the primes. And you have to understand that this was at the time, in other words, it was 2's alternating with primes. 2, 2, 2, 3, 2, 5. I wouldn't have jumped to that conclusion, you understand, if it said 2, 1, 2, 3, 2, 5, 2, 7. But it didn't start out 2, 1, 2, 3. It started out 2, 2, 2, 3, 2, 5. It was as if God was handing me the primes on a silver platter. And so I, well, I guess it makes transparency. I should explain something. Good enough. That was my reaction. Okay. Now, again, I was working on a computer that had about 10 digits of accuracy. So I was losing accuracy. I knew I was losing about a digit per descent. So pretty soon I knew that I wasn't going to be able to trust the thing. And I had to get out a triple precision arithmetic function thing. It was a package of cards. Of course, this is all done on cards. A package of cards, like 300 cards long, that was in machine language that you would put behind your program, and you would have to rewrite the program so that where it had a plus sign before, you would then say something like triple plus of the 2 arguments. And you would have to write things in this complicated way. But you could get it to do arithmetic in triple precision. And so I got it to do arithmetic in triple precision. And then that's what came out. The odd numbers, God made a mistake at the beginning. And so it's 2, 2, 2, 3, 2, 5, 2, 7, 2, 9, 2, 11.
But if you're an engineer, it's still okay.
So I don't know. It was exciting and disappointing at the same time. There was beauty, but there was sort of obviously a big disappointment. But this was the kind of thing that I was very hooked on, and this is the kind of thing that led me on to make more explorations. Now, what I wanted to talk about is what I mentioned earlier, that the square root of 2 and phi, the golden ratio, were sort of complementary numbers. That is, the sep column of 1 was this count column of the other, and vice versa. So the question is, what would be the complementary number to E? What real number, which would be between 2 and 3, but it would be closer to 2 now than to 3, would have this be its sep column and this be its count column? What real number would have that property? And in general, for any alpha, what real number would have the property that there'd be some other number that would have the property that it was the flip, what I call int. So that was my notion that if int is when the count of 1 is the sep of the count column of 1 is the sep column of the other, and vice versa. Okay, so obviously it's a function of its own inverse, and that was my definition for int. And so again, as an empirical mathematician, I plotted all the points that I knew, and I got a picture that looked something like that. That was my first graph of int. Just a handful of points, or a couple of handfuls. And I could see some kind of structure there, but I didn't know quite what to make of it. The line is just y equals x, but it's the dots that are the interesting graph there. This is int between 1 and 2. Between 2 and 3, it would look identical. because it's just, the whole thing is just transported up sort of periodically. You just move to the right and move up. So what it does between any pair of successive integers is all that matters. So this was my first graph, and then I asked the computer to give me some more points, and well, I guess this is maybe not more points, but I just sort of drew a wiggly line. No, I guess there's a few more points. There's a few more points up in this zone here. I guess so I probably added another 10 points here, and I got some wiggles. And I was curious about this kind of wiggly function, and so I wanted to know what happens here. Well, I can either point up there or down here. I wanted to know what happens down in the corner because I didn't have a clear sense of it. So I got more numbers. Oh, this was number crunching. There were no plotters. No plotters at all. So I got out the numbers, and I saw more wiggles. And so I was interested. It seemed like I was getting some sort of wiggly thing by the tail. Well, to make a long story short, when you plot it, this is done much later. This is done in the 80s. I was just trying to reconstruct this is done on the map. I was just trying to reconstruct what I did back then. And I got graphs that were of increasing amounts of precision, not precision, but fine grain. And so I could see that it looked as if it was composed of structures, sort of a pattern here, and a pattern here, sort of a line, and things like that. So I was interested in knowing, I'm looking at the structure of each of the parts, so like that one. So I would then have the computer explore that area in more detail, and it looked like that. And then I was interested in knowing, what does that look like? And it looked like that. And so I caught on at this point that I was dealing with a structure that was basically it was composed of copies of itself, but the copies were slightly distorted. They were kind of warped, you might say. And here is a more detailed graph where you can sort of appreciate the structure. You can see what it looks like, and you can easily imagine exactly how it is. And this was very intoxicating to me when I was on the order of 17 or 18. And so I asked myself some questions at this point. One question was, well, int of any rational number, to define it for rationals is a little tricky. But you can define it for rationals, and int for any rational number is another rational number. That's a trivial thing. Sort of the second count sequence is the finite. And so you run out of gas, and then you interchange them, and you work backwards, and you get a rational number. So then, it turns out also that the second count sequences are actually intimately related to continued fractions. They're cousins of continued fractions. They're which I'm not going to go into, but some of the theorems that hold for continued fractions also held for these things, which was that if you are dealing with a quadratic number, such as the square root of 2 or 5, then the count and subsequence are periodic. They repeat. So 1, 1, 1, 1 is a very, very short period, but they can be longer, but they will eventually, for any quadratic, it will repeat. And so if you interchange them, they're still periodic, and so if you work backwards, you get a quadratic as int. So if alpha is quadratic, then int of alpha is quadratic. So I wanted to know what is the case for a cubic, or for a transcendental number, or just in general, an algebraic number. So I put in cube root of 2. And I took int of it to, I don't know, many decimals, probably triple precision. I probably got out 15 or 20 decimals, I don't know. And then being an empirical mathematician, I then substituted it into a whole bunch of cubic polynomials with integer coefficients systematically. I mean, I generated it. I had a program that generated these polynomials and then stuck this number in to see if it was cubic. And it never seemed to be 2. It never came out 0. And so this was very puzzling to me. I thought